right. I am here right now with Przemyslaw Wirkus, who's a principal engineer at ARM. How are you doing?
Yeah, hello.
Cool. So ARM is really cool. It's really grown a lot in recent years.
That's right.
And just to kick things off, since we're going to be talking a lot about ARM, what are some of the challenges that come with measuring performance for it?
So the most critical part is to have the right tools for the right job, select the right workloads to measure your performance, and also understand how it all fits into the Windows on ARM ecosystem. Today I would like to present the tool that we developed in ARM called WindowsPerf. This is the microarchitecture performance analysis tool. Together with the ARM's telemetry solution methodology, we implemented the top-down hotspot methodology inside the tool. We can actually follow steps that were precisely defined by our architects to actually measure the performance. And today I would like to show you and maybe execute WindowsPerf on our 𝗦𝗲𝗶𝗸𝗀𝗁 Windows on ARM machine that I just logged into. And I would like to show you how we step-by-step do the top-down analysis, how we use the new and existing tools like top-down tool to do that automatically. And also I will showcase how we actually fit into the Windows on ARM performance ecosystem. Because we don't want to reinvent the wheel, we just build enough so you can get what you want. Everything else is already there from Microsoft.
I like that. Work smart, not hard.
That's right.
Do just enough for people to get to fixing their problems. So we're going to kick things off, it sounds like, with the demo, right?
Yes, just a little bit of the introduction. You can go to the ARM developer webpage to read about the telemetry solution, top-down methodology, and much more. You can also visit our WindowsPerf webpage just to get our software release, binaries, and also read about interesting stuff. We also link other documentation like ARM learning path and ARM CPU telemetry solution data. I will later also show you how I actually follow the top-down methodology. We actually define also metadata in a JSON format that actually describe events and metrics and groups of metrics, so we can actually just follow steps designed by the architect. This JSON file we also include into the WindowsPerf. At the bottom of it, there is a section called methodology, and I will just follow the steps described by this. I will just follow the cycle accounting, group of metrics. I will see where our workload. We're gonna work actually on a C Python native ARM64 workload. We're gonna compute Googleplex. I'm gonna follow the steps manually to explain what's happening, and then I'm gonna run the top-down tool from ARM to show you how we can automate that process. And after that, I will go a little bit deeper. We're gonna do a little bit of the sampling to show you where in the source code exactly your hotspot could be. So let's start. I have some helper document to help me with the commands.
Because you're not going to memorize all of those?
I don't memorize them. They are automated. But what's going to happen quickly is I'm going to do the WPerf stat command. We're going to count. Minus -m stands for the metric. We're going to pick up the group of metric. It's all implemented and baked into the WindowsPerf. On core 7, we're going to run CPy10. And the -c 10 to the power of 10 to the power of 100. We're going to evaluate this. We're going to run this for 10 seconds. So while we are running this, I can explain what's happening. We are now performing the static performance analysis. We're going to run the workload, collect the data, and after the workload finish, we're going to analyze actually what we learned.
Cool.
So it's not a real-time analysis. And our workload is also designed to exploit certain algorithm or a module that we are trying to optimize, because this is microarchitecture performance analysis or profiling, not the whole application.
Cool.
For that, there are different tools, yes.
Awesome. So microarchitecture profiling is getting kind of nitty-gritty.
That's right. Getting inside the CPU nitty-gritty details and understanding which parts of the CPU are actually lighting up when your workload is running. You can actually passively observe if you, for example, you're running vectorization, or if the crypto instructions are running, or maybe your load store speculation is on a heavy side.
Okay.
We're going to observe this with the workload, but the first step in the top-down analysis is to actually look from the very high point of view on the workload. We're going to look at the front end and the back end of the CPU. Just quickly, front end of the CPU is like a pump that's trying to suck all the instruction in the CPU and speculate which one I actually should get in advance. Whereas the backend is the conveyor belt that actually transmits all the instructions later and actually perform the computing. So the backend, you will actually you are mostly interested about the data, whereas in the front end about the instructions themselves and the decoding. Here at the bottom, you can see that for the telemetry solution metrics, we see that the backend is heavily, or maybe not heavily, but is used much more frequent than the front end. So we can actually start zooming in at the backend. And because in that JSON I already checked what are the groups of metrics that we actually should inspect to look at the backend, I was just gonna do that automatically from my little tiny helping list of the commands.
So that analysis came up pretty quickly too. Is that the norm or?
Yes, that's the norm because workload is usually very small.
Okay.
Because you want to run it in a reasonable amount of time to just saturate enough events. And please remember, this kind of CPUs are running like 3 gigahertz. So it's billions of instructions every second. So it's really enough to look at what's happening. Also, performance engineers will actually adjust the time and the workloads independently. But that's another set of problems that one has to solve. Here we have a very simple workload.
Gotcha.
We're not going to worry about that much, but it's a very good question, actually. So we're going to run this command a little bit more complicated because after -m, I have many more metrics. I'm going to run exactly the same workload. The same things will happen in the CPU. I did not change anything, right? It's also very important when you are running a workload that workload has no external state. It will not read a file, it will not check the time. It's always the same piece of algorithm or a module doing exactly the same thing.
Awesome. And you're able to analyze just the front end or just the back end, right?
That's right. Usually you own the code you are actually profiling. So in general, we know what we are looking at. We just want to understand exactly where maybe not where we make mistakes, but where we can actually improve, right? Or what we can actually change to make that workload better. Please also note, I'm not actually measuring any time here. So I don't care how fast the workload is running. It's actually continuously doing the same computation of 10 to the power of 10 of our 100, right?
Right.
So, okay, so I finished the analysis now of the backend metrics. I actually use the multiplexing of WindowsPerf. It's a very nice feature that allows you to measure many events at the same time. Because in general, you only have few registers to actually latch those events. But we are actually multiplexing. So what we are doing here, we can quickly just look at the list. And at the bottom, actually, we can see that mostly load speculation, store speculation,
Integer DP?
integer double precision speculation. These are the dominant. And we're actually expecting that because we're actually just taking integer numbers and we're actually multiplying them a lot.
Oh, boy, yeah.
And how Python works, we are actually calculating very, very big number. It will grow in memory, right? So we're expecting the loads and store will be dominant. And indeed, they are taking around 35% of all the speculative instructions. It's actually very useful to understand. Also, when you look at this kind of a set of metrics, you can see here, for example, that there is no, for example, scalar floating point operations is actually good. We don't want to use floating point just to compute integers because they are slower on every architecture.
Right.
On every architecture. Let me try to also go deeper. Let me see what I can do. Okay, so I already understand. I have few speculations that I can look at. So now let's go deeper. I will actually look at the load speculation. Our favorite test event that we test all the time is the load speculation. So now I would like to understand with sampling, I'm gonna now change the way I'm actually measuring things. I went from counting stuff to actually sampling. Sampling is actually a process, I will call it, it's a statistical process. So we'll now use maybe some statistical methods to actually understand where we are actually hitting in the source code all these hot areas.
Perfect.
I will just annotate at the same time because we don't have so much time to actually show everyone. I will do something very similar to what I did before. By now you can see I will do the -e LD spec. I will just try to see when my event counter saturates, where I actually hit the program counter. I'm gonna also correlate this with the lines of code. Actually, I can talk about this when we actually do it. So I can correlate this, and actually I can understand where in the source code I'm gonna actually hit some bottlenecks.
Yeah.
Because what we want were the hotspots in the source code for developers.
That's important. We don't want to do all the trial and error for things that
That's right.
have nothing to do with
That's
the
right.
issue. Yeah.
So we did this analysis because we have this CPython build with the debug information. I have all the information about all the symbols, all the functions, and the DLLs it's calling. So I can see that 79, or maybe 70, yeah, 79, in this case, 79% of all the maybe hits when we saturate the LD spec event actually happened in the xmal function in the Python DLL. It's actually a good news because we are multiplying, and this function, it looks like it's multiplying, and actually we checked and it is multiplying. So how you can actually go even deeper. You can actually disassemble to see which instruction exactly is being the one that is causing the problem. But this is sampling in software, so there is a little bit of inaccuracy. We will eliminate that because we're gonna implement the ARM SPE, which is sampling in hardware. So I can actually move to something a little bit different. I want to show you how we implement all this stuff with the ARM, with the Visual Studio GUI. We have extension that does exactly the same thing. We can run the sampling or we can run the counting, and it actually gonna show you in your source code where are the hotspots.
Oh, perfect.
It's very useful.
Yeah, super useful.
Especially when you just have a smaller app, you are open source, you have a microtransaction. It's easy for you to just run this from Visual Studio. It is ecosystem.
Or if you're not someone who likes to use the terminal.
That's right.
Too, right?
Not everyone likes to use a terminal. Why we have WindowsPerf also as a terminal application? Because we are actually LinuxPerf inspired. We want the performance engineers to actually join Windows on ARM performance analysis, and it's a very easy way for them to actually join. You can see here at the bottom, we have the disassembly that I didn't show you from the command line because it's a little bit hard to see, but we have the disassembly. What else we can do? We also can use the WPA, which is the Windows Performance Analyzer. We develop a plugin that reads the WindowsPerf JSON output. It processes it, and we can use the WPA, which is a Microsoft tool that is used by everyone that does performance analysis.
Oh, great. So you have that Windows ecosystem.
That's right.
Integration.
So we integrate. We don't develop something new.
Right.
If there is a visualization already available, we just attach ourselves to that with that adapter.
Yeah.
And that's what we did.
If it ain't broke.
Yes. And no one has to learn anything new. And this is just an example of me showing you different metrics and different events that I just captured running a different workload, actually. It's a different workload, and over the time, with the timeline, we can actually see how it works. So that's one of the other highlights of this solution. Yeah, I think in general, that's all I wanted to show.
Cool. You're so casual about that. That's all I wanted to show. No big deal. Like
it was a fast track for performance analysis. Performance analysis is not easy, even for advanced performance engineers. I think that's all the key takeaways.
Cool. Thank you for sharing that. I mean, performance is so important to so many people, and making it easy to detect those performance bottlenecks is so important.
That's right.
So what's next for WindowsPerf?
So what's next? We're gonna add ARM SP support, so hardware sampling. Why we didn't add it now? Because not every ARM CPU has actually that feature baked in. For example, mobile devices will not have, but my server workstation does, right?
Right.
So you want to have the software solution just to have sampling, and then you have one in hardware for your server solutions. Other things that are coming is we're going to actually integrate with the ETW, extended trace for Windows, so you can actually inject all this data directly into the ETW, which is the right way to go. We are again tapping into the Windows performance ecosystem.
Great. Well, I'm excited to see what's going to be happening next year's build. Shoot. So, Przemek, thank you so much.
Thank you very much.
Yeah, and if you're interested in learning more about ARM, go check out the booth. If you're here, you still have a couple hours. If not, no worries. Go to the featured partner directory and check them out there. Thanks again, Przemyk.
Thank you very much.